Hello everyone. So yesterday we talked about first order correction to the energy. Okay. So we obtain the first order correction to the energy by the unperturbed wave functions. Unperturbed wave function means psi n psi n zeroth order correction to the wave function. So we are building that. So by that we construct the we obtain the first order correction to the energy. Today we'll first let's solve an example based on the first order correction to the energy. Okay. So here given unperturbed wave function for infinite square wave potential, or this is the unperturbed wave function. Okay. But there is no unperturbed wave function means zeroth correction to the wave function. Okay. So there is no perturbation to that wave function. When perturbation happen to the any potential, so the potential will be changed. Okay. Like yesterday I shown one figure. The when perturbation happen to the one system, one infinite square wave potential system, then there is a one bump came into that picture. There is one bump like a speed breaker. Okay. So like that now here one example is given. suppose the first Suppose that we perturb the system simply the raising the floor of the wall by a constant amount v naught. In that case, h prime means perturbation, which is equal to v naught, and first order correction to the energy of the nth state is, see, here is given. So this is the potential. This is the infinite square wave potential. This is the infinite square wave potential. Let's say it has a width of a. The potential well has a width a. Okay. So now perturbation. So this is the v of x. Okay. So for infinite square wave potential, the perturbation is happened. So the potential is raised up to the v naught. Now here asking the first order, what is the first order correction to the energy of nth state. Okay. So how to find it? So yesterday we derived that the formula for nth order correction to the energy of nth state, to the energy of the nth state is inner product of psi n power 0 v naught psi n power 0. This is the inner product. Actually we have find out En first order correction to the energy of nth state, which is equal to inner product of psi n of 0th correction h prime psi n power 0 of inner product. There is the inner product. Okay. So here is in this example, the perturbation is happened in this case, the perturbation is equal to v naught. Okay. So we perturb the system by simply raising the floor of a well by the constant v naught. So h prime is equal to 0. H prime is equal to v naught. Okay. H prime is equal to v naught. Okay. So yesterday we have derived hn first order correction to the nth first order correction to the energy of nth state is inner product of unperturbed states with having perturbation. Okay, so keep h prime is equal h prime is equal to h prime is equal to 1 v naught. So v naught. Okay, so here v naught is a constant one, so you can take it out from outside. So inner product is nothing but like a dot product of two vectors in a classical mechanics. In quantum mechanics, we'll call it as inner product. So if you do the inner product of any two wave functions, you will get a scalar quantity. Same as in the dot product also, if you do the dot product of any two vectors, you will get a scalar quantity. Okay, so inner product of same wave functions gives rise to 1. Okay, understood? You can do in another manner also. Sorry. If you want to solve this equation by integration, so En prime, which is equal to integration psi n of 0, okay, v naught, this is the complex term, psi n power 0 into dx. Okay, so write the unperturbed wave function of infinite square well here, okay, which is equal to root over 2 by a whole square integration minus infinity to plus infinity. Is not minus infinity plus infinity, we are solving from 0 to a. We are integrating from 0 to a, because the width of the potential is 0 to a. Okay, then sine square n by x by a into dx into v naught. Okay, here v naught is there, right? So v naught. Actually, in the first step, in the before step, there should be a h prime. H prime means unperturbed Hamiltonian. In the place of h prime means perturbed Hamiltonian, we are writing the v naught. So inner product is nothing but we can write in the integration form also. So the inner product means ket. This is a ket, right? This ket notation simplifies the mathematical derivation. If you follow the integration procedure, it gives some more steps. It gives more steps to get to reach the solution. Okay. So now the potential is changed by the half of the potential. Now potential is changed like this. In the previous problem, the potential was like this, is raised by constant value v naught. Now the potential is changed to the half of the potential only. So v naught up to a by 2. Next, from a by 2 to a by 2 to a, the potential is constant. Okay, there is no okay. So So total energy which is equal to unperturbed wave function, unperturbed energy plus perturbed energy, first order correction to the energy. So what is the form of the unperturbed energy of the infinite square wave? N square pi square h cross square divided by 2m a square plus v naught. This is the total energy for the perturbed system. Okay. See, the corrected energy levels that are En is nearly equal to En of zeroth correction to the energy and first order correction to the energy. First order correction we got V naught. They are simply lifted by the amount V naught. Of course, the only surprising thing is that in that case the first order correction is the exact answer. So now the perturbation extends only the halfway across the well. Okay, that means from 0 to A the potential is raised up to constant value V naught. From A to A by 2 to A the potential is not raised, is not perturbed. So for that now you can write integration first order correction to the energy, which can be written as 0 to A for zeroth correction of to the wave function h prime psi n. This is a star complex number of 0 into dx. Okay, which is equal to, so root over 2 by a whole square 0 to a by 2 sin nx pi by a whole square. So 0 to a the perturbation is equal to V naught. Okay, from plus again you have a term 0 a by 2 to 0 a by 2 to a integration from a by 2 to a. Again the perturbation is 0 because the potential is not raised up to any value. So from 0 to a by 2, from 0 to a by 2, from 0 to a by 2 the potential is raised up to V naught. So potential is perturbed. From a by 2 to from integration from a by 2 to a, there is no perturbation. So h prime is equal to 0. So only integration is exist from 0 to a by 2 only. The integration doesn't exist from a by 2 to a. Understood? Okay, so if you solve the integration from 0 to a by 2 sine square n pi x by a into dx, you will get a. This a cancel out, you will get a by 4. Sorry, you will get a by 4. This a cancel. Let me write it here. If you solve this integration, you will get the result as a by 4. This a by 4 2v naught by a. This a will cancel out, 2 cancel out. So you will get v by 2. Okay. That's the result. So let me solve the so far we have discussed so far we have derived the equation first order correction to the energy. Let's solve the first order correction to the wave. So let's start with the first order correction, the equation of first order correction. to the energy. Yesterday we have derived this equation. This is the 6.9 equation. See it in the yesterday's class. Okay. So solve it from start it from first order correction to the energy. Okay. Right side is a known function because we know the unperturbed wave function, right? For the infinite square well, we know the unperturbed wave function for the infinite square well. So that's why the right side term is a known function. Okay. So in the left hand side we can know h naught and en of 0, right? So this amounts to a inhomogeneous differential equation for first order correction to the wave function. Now the unperturbed wave function constitutes a complete set. So first order correction to the wave function of nth state can be expressed as a linear combination of them. So when this unperturbed wave function can constitute a complete set, when this when these wave functions obey the orthonormality. Okay, then this wave function can constitute a complete set. When will this wave function constitute a complete set? Only happens when the inner product of the inner product of psi m into psi m, which is equal to 1. This is the orthogonality. It satisfies the orthogonality property. Then orthonormal property. Then it constitutes a complete set. Okay. So can be expressed as a linear combination of them. So now we can write the first order correction to the wave function is equal to summation m not equal to n psi m powers n psi. So zeroth correction order of zeroth correction to the wave function of nth state. Okay. Second. One second. So use the unperturbed Schrodinger equation 6.1. So this equation 6.1 is in the previous class. So once go back to the equation 6.1. Okay. So substitute substitute the first order correction of n is equal to summation n not equal to m and psi m of n psi n of 0. Okay, n of 0 psi n of 0. Substitute this expression into the previous one. Where we started. So take the inner product with the psi zeroth correction to the wave function of the health state. Okay. So take the inner product on both sides. So here minus minus plus. Okay. If L is equal to n, so if L is equal to n, what will happen? L is equal to n. L is equal to n. First take the right hand side. So inner product of psi L of 0 of psi n of 0. So inner product of these two functions will equal to 0 because these two wave functions are different. These two wave functions are different. So when will this inner product will be equal? When L is equal to n, then the value become 1. Okay, so if see here, L is equal to n, then the inner product will be 1. Here L is not equal to, so inner product of state L and state n is not equal, so it will be 0. So right hand side becomes 0, left hand side becomes, so equation is end up like this. En first order correction to the wave function of nth state, which is equal to inner product of psi n power 0 okay. This is the first order correction to the energy if L is equal to n. Okay. If L not equal to n, L not equal to n, what will happen? If L not equal to n, this inner product will goes to 0. Okay. So you have only the two terms, which is one term in left side and one term in the right side. Okay. And L is not equal to n, but L is equal to n. Put L is equal to n. Then this inner product goes to 1. Okay. Then here m becomes L. Here n becomes L. Here L becomes n. So you will end up with this equation. So so rearrange the term and then Cem power n, which is equal to inner product of with unperturbed wave functions with perturbed Hamiltonian divided by difference of perturbed energies. Okay, so this coefficient substitute this coefficient in psi n prime, which is equal to integration of Cm of n not equal to n Cm prime of 0. Okay, substitute this coefficient in this linear combination of all unperturbed states. Okay, then you will end up with this equation. This tells that the first order correction to the wave function. Okay, so if m is equal to n, if m is equal to n, the denominator becomes 0, then now the wave function becomes infinite. Okay, understood? So this that's why there should be n not equal to n. There should be we should get finite value in the denominator. Okay, I hope you understand this today's lecture. Okay, today today or the day after tomorrow we'll see the second order correction to the energy. Okay, thank you.